In this new section, we're going to be talking about reduction of order. Basically, we'll say take a second degree differential equation and reduce it to a first degree differential equation, a linear differential equation. Now, suppose that you are given that y1 equals e to the x is a solution to y double prime minus y equals 0 on the whole number line, from negative infinity to infinity. And we want to use reduction of order to find a second solution, y2. So what you do is you start off with y equals u of x times the y1 of x. In our case, u of x times e to the x, because y1 is e to the x. And you want this new solution to satisfy this. That is, we have to calculate the second derivative and take away y from that. So y is this. Y prime will be, for now on, I'll just write it as u e to the x. So y prime is the derivative of the first factor times the second, which is e to the x, plus just the first factor times the derivative of e to the x, which just happens to be e to the x. The second derivative, I'll take the derivative of this, and then I'll add on the derivative of that. The derivative of this, the product of two functions of x's. I'll take the derivative of u prime first, times the e to the x, plus I'll keep the u prime, and I'll take the derivative of e to the x, which is e to the x, plus now I take the derivative of u, I get u prime times e to the x. I already have that, so now I have two of them. Plus, I'll keep the u the same way, and I'll multiply by the derivative of e to the x, which just happens to be e to the x. Now, what is y double prime minus y? What is this? Take away that. Well, I have this, and I want to take away u e to the x. Okay, fine. So I have u double prime e to the x plus 2u prime e to the x. In fact, I can factor out the e to the x. And I have u double prime plus u prime. And we know that this equals 0. And after all, that was our differential equation. So this times that equals 0. 0, well, we're in an integral domain. If our product is 0, either this is 0 or that's 0. But e to the x is always positive. After all, it goes like this. This is where y equals 0. So y-axis, or the equation x-axis, or the equation y equals 0. Say it again. I'm sure you know it's the x-axis. The equation of this line is y equals 0. These y values are all bigger than 0. They're all bigger than 0. In particular, they're not ever 0. So if this times that equals 0, it must be the that equals 0. Okay, so our goal is to have u e to the x being our second solution. The only thing is we don't know what u of x is. So we're going to figure out what u equals. And use reduction of formula. If I let v equal u prime, well, if v is equal to u prime, if I take the derivative of the left side, I get v prime And if I take the derivative of the right side, get u double prime. And that's equal. The equal sign is valid. So this is v prime plus 2 u prime is v equals 0. Okay, that's our reduction of order. We went from the second degree differential equation to a first degree. And this first degree is pretty simple to solve. V prime plus 2v equals 0. V prime plus 2v equals 0. I'll bring that to the other side, and I'll write that as dv dx. This is negative 2v. Now this is separable. I'll keep the dv where it is. I'll bring the v to the bottom on the other side. I'll keep the negative 2 where it is, and I'll move that piece. It's just moving pieces around. The pieces better are called factors. Now I integrate both sides. The integral of the left side down to v. The integral of the right side is negative 2x plus c. There's a little e down here. E to that power. E to the negative 2x plus c is equal to v. But remember, this is e to the negative 2x times e to the c. The e to the c is some constant. So it's e to the negative 2x times c. But you know what? I'll put the c first. So that's what v equals. But remember, v was u prime. Okay, so this is where, this here is where u prime equals. And I'm anticipating another constant, so I'm going to call these C1. So we now know that u prime is c e to the negative 2x. But remember, we want to find out what u is. We want to find out what u is, multiply it by e to the x, and then say we have y2. Okay, maybe we should call out y sub 2. Okay. Well, u is du dx, and it equals to c e to the negative 2x. I'll just move this to the top on the other side. C e to the negative 2x dx. And then I integrate both sides. The integral, and this was c1. The integral of the left side is u. The integral of the right side. Well, the c1 comes out. See, we're in front. This is really c1 times the integral. Now remember, the integral of e to any number times x dx is nothing more than e to the kx, and then you divide by that k plus c. So I get e to the negative 2x over negative 2 plus a constant. Call it c2. But this division is another constant. I'm still going to call it c1. So it's c1 e to the negative 2x plus c2. Now, I claim that this is the u value. Now, this u value was supposed to satisfy this equation. Let's check it. U double prime plus 2u prime equals 0. U double prime plus 2u prime equals 0. And we claim that u was c1 e to the negative 2x. Plus another constant. Okay, so let's calculate the two derivatives and move on. U prime will be negative 2c1 e to the negative 2x plus 0. U double prime will be 4 c1 e to the negative 2x. How am I getting these answers? The derivative of e to any number times x is e to that number x times the derivative of the power, which is always that number. So kind of all that happens is the power comes down. The power came down, multiplied by the constant in front, that 4ci. Because I have u prime underneath that line, and 2u prime, well, this is u prime, I double it, I get negative 4c1 e to the negative 2x, and when I add them, the left side stays this, and the right side is 0. Got it. That's what I wanted. I really do have the right u. I checked it. You want to do the check on an exam or homework, fine. Now, we said that y2 was u times y1. Well, I have u, and I'm not going to try to memorize. I'm going to go back and look. y1 was e to the x. y1 is e to the x times y1. And there's your solution. And if we were, you can FOIL it out if you like. Now, we can check to see if this works. We can check to see that we didn't make a mistake. And on that note, I will multiply it out. This is what y sub 2 equals. And it's supposed to satisfy, the lack of space, let me put it here. Y double prime equals y. That is, y double prime minus y is 0. Well, y2 prime will be negative, because there's an understood negative 1 there. It'll be negative 1 c1 e to the negative x plus c2 e to the x. That derivative doesn't change. The second derivative will be positive 1 c1 e to the negative x plus c2 e to the x. Well, if you notice, they're the same. So of course, y double prime minus y will equal 0. Okay, so the check wasn't bad. And I believe that students should check their work. That way you know if you're right or not. You leave an exam, you say, oh yes, I got that problem right. Well, you know what? I tried my best, but it didn't work out. Now, let's talk about the general case. You have y double prime plus a function of x times y prime plus a function of x times y equals 0. Now, I'm going to derive the general solution to this, and then life will be sweet. Suppose y1 is a solution to this equation. So, y1 double prime plus p times y1 prime plus q of x, I'm not going to write the of x, times y1 equals 0. All I did was replace y with y1. Or if you prefer, I replace y double prime with y1 double prime, and y prime with y1 prime, and y with y1. As before, we defined y to be a function of u of x times y1 of x. which is just u times y1. Okay. Well then y prime will be, let me do it here to save some space. Y prime will be u prime y1 plus u times y1 prime. The second derivative, so I'm going to take the derivative of this. First, of course, I'll take the derivative of that, and then I'll take the derivative of that, and then and only then will I add. So the derivative of u prime y will be u double prime y plus u prime y prime, plus the derivative of this, which will be u prime y prime, so I'll have two of them, plus u times y double prime. And all these y's are sub 1. So now I want to write down this equation using this information. For y double prime, I'm going to put this. Here goes. Y double prime plus p times y prime, u prime y plus u y prime, plus q times y, which is uy1, equals 0. Okay. Now, u double prime y1 plus 2u prime y1 prime plus u y double prime plus, I'll distribute the p, u prime y sub 1 plus pu y sub 1 prime plus qu y1 equals 0. Okay. I really didn't get much doing that. But what I'm going to do now is, I'm going to combine the terms that just has u's, those three. So I have u times y1 double prime plus p times y1 prime plus the last one, which is q y1. I factored out the u in front. So I underlined what I already used. So I'm going to write down everything else from right to left. That is, first I write this down. And you don't have to, I'm just doing it that way. Plus this piece. And I take it, that's it. Okay. And we know this is 0. But this piece here, the first piece is also 0. Because remember, y double prime plus y prime plus py prime plus q y1 equals 0. This piece is 0. And when I multiply it by u, it's still 0. So 0 plus this is equal to 0. Well, then this is also 0. U double prime y sub 1 plus 2u prime y1 prime plus pu prime y sub 1, that's 0. Now this equation is 0. But this equation is separable. This equation is 100% separable after you do a reduction. U double prime y1 plus 2y prime u plus py1u. I might have written it down in different order. It was from memory after all, but I wrote this down on the other page. What I mean by different order, maybe I interchange the u prime and the y prime. Maybe the p, u prime, and the y are now in a different order, but that doesn't matter. Now, what I can do here is I'll group the u prime double primes and the u primes together. So I have u double prime y1, and in the second bracket, I'm going to factor out the u prime. So obviously I have a typo. Now if you notice, both the u and the y sub 1 are prime. So let me do that up here. They're both prime. Make sure the other one is the same. Just the u is prime. Okay. So now I can factor out the u prime, and I get 2y sub 1 plus py1. And this is 0. This is where we use the reduction of order. I'm going to let v equal u prime. So then that will be v prime. So v prime y1, u prime is just v, plus v times 2y1 plus py1 is equal to 0. Now this is separable. This is separable. I'm going to bring this piece to the other side. V prime y1 is negative, and I'm going to even distribute 2y1. Actually, I'm not going to distribute. I'll just write the v at the end. Now, I'm going to bring this v. So this is really dv dx y1, and it equals to negative 2y1 plus py1. And notice that it's 2 times y prime. That should be a prime times v. So this is separable. I am going to move this, and that. The dv will stay, but this will come on the bottom. The negative 2y1 prime plus py1 will stay. So let's see. This I dealt with, it's right there. I dealt with this, it's here. I dealt with all of this. And now the dx, I'll move up here. And the y1, it goes in the bottom. In fact, each term gets divided by y1. Okay. So right now, I have dv over v, which I know how to integrate, is equal to negative 2 over y1. Now, y prime is dy dx plus p, the y1's cancel, dx, which is negative. I'll distribute this dx. You have 2 over y1 dy dx times dx, which cancels, plus p dx. Okay, I'm gonna have to erase stuff. Now I'm going to integrate both sides. The integral of the left side is ln of v. The right side, let's distribute, here's that minus sign, I'm going to keep it out. Let's distribute the integral. The integral of this, 2 over y1 dy, the integral of that, plus the integral, dy1, plus the integral of p dx. Okay, so we have ln of v is negative. This first integral, 2 over y1 dy1. I can pull a 2 out in front, and I get dy1 over y1. Well, that's 2 times ln of y1. 2 times ln of y1 plus the integral of p dx. In fact, this 2 can come up as the power. In fact, let's do that. The 2's up there. So I have ln of v minus, I'm going to distribute, equals negative y1, ln of y1 squared. I'm distributing that minus the integral of p dx. I'm going to bring this to the other side. Then I have ln of v plus ln of y squared equals this. Negative integral of p dx. And we're getting there. Ln of one thing plus ln of another thing is simply ln of the product. And this is negative integral of p dx plus a constant. Now remember, ln is shorthand for log base e. E to this, e to the negative integral p dx plus c is equal to what I'm taking the ln of, vy squared. This plus c, let's even call it c1, just comes in front. It comes in front. Okay, so we're almost done. We are almost done. Let us write down what y equals. I meant to say what v equals, sorry. Dividing both sides of this equation by y sub 2, we have v is c1 times e to the negative integral p of x dx all over y1 squared. For v, but v, if you look back, hopefully it's there somewhere, v was u prime. V was u prime. So u prime is equal to this. But I want to know what u is. I want to know what u is. If I integrate the left side, I get u. I integrate the right side, I get the integral of the right side. Okay. Now, y sub 2, the second solution to the homogeneous equation, is y1 times u. Well, here's y1 times u times this. This here is the formula to get a second solution to a homogeneous equation if you have one of them. That's the formula. All of that just to get this formula. Okay, so now Suppose you come to know that y1 equals x squared is a solution to x squared y double prime minus 3x y prime plus 4y equals 0. And we want to find the general solution of this differential equation. We want to find a general solution. So, find the general solution. So let's find the second one. Well, we know that y2 is equal to y1, that formula that we just derived, this baby right here, is equal to c1 e to the negative integral p dx over y1 squared dx. The only thing I'm going to comment is we can let the c1 be 1. We can just use 1. So I'm going to do that right there. Now, for this to work, we're going to have to divide by x squared. We're going to have to divide every term by x squared. And because we want to have y double prime, not 3y double prime or x squared double prime, just y double prime. This is 3 over x y prime plus 4 over x squared times y equals 0. That there is p of x. For the record, that's q of x. That there is p of x. Okay? So y sub 2 is y1, which is x squared. That was given, times the integral of a fraction. E to the negative integral of negative 3 over x dx over y1 squared. We have x squared in front, integral. In the bottom, we're going to have x to the 4th. Now, negative the integral of negative 3 over x dx. If I factor out the negative 3, I'll just have 3. And I'll have dx over x. The 3 is the 3 times that, which is ln of x. Which is ln of x cubed. I'm going to bring this up. So I have e to the ln of x cubed dx. I have x squared in front. Now remember, e to the ln of anything is the anything over x to the 4th dx. X squared not being a constant. I can't bring it in and out of the integral sign. This fraction is 1 over x. And if you want to write the 1 over x dx as dx over x, go for it. But no matter what, that's ln of x. So you get x squared times ln of x. And that is another solution. Now, the general solution will be a linear combination of the two. A constant called a c1 times y1 plus a different constant times y2. I should be saying y2 equals. So y2 is c1 times y1, top left corner, y1 is x squared, plus c2 times y2, which is x squared ln x squared. Just ln x, excuse me. And this here is not y2, sorry, we'll call it yg for general. That's a general solution. Linear combination of solutions are also solutions. Y general is a multiple of y1 plus a multiple of y2. So that there is the general solution. Try another topic. Suppose you come to know that y1 equals 1 is a solution to the associated homogeneous equation 2 y double prime plus y prime equal 1. Okay. Now this equation, y double prime plus y prime equals 1, is not homogeneous. The homogeneous equation associated with that equation would be y double prime plus y prime equals 0. And this is a solution to that. If y1 is a constant, then y prime will be 0 and y double prime will be 0. And yes, 0 plus 0, it really does equal 0. So it certainly is a solution. Now, we want to find a second solution to this homogeneous equation, and after that, to find a particular solution to the non-homogeneous equation. This is two parts. Find a second homogeneous solution, and then find a particular solution to the non-homogeneous equation. Now, we know that y2 is equal to y1 times the integral of e to the negative integral p of x dx all over y1 squared dx. Now, remember there's a 1 here, and that's p of x. And y1 is also 1. So these are 1s, and 1 squares are 1. Multiplying this integral by 1 doesn't do anything. And before you can integrate, you better calculate what you're integrating. And dividing by 1 squared, which is also 1, is meaningless. So the only thing that really survived is the top half of the integral. This integral of e to the negative p of x, which is 1, dx. And the integral of negative 1 is negative x plus a constant. I'll call that constant c1 dx. But it keeps coming up and up again. I can put that constant in front of e to the negative x. But I want to integrate that dx. And this is just going to become negative c1 e to the negative x plus another constant. Of course, you can just call negative c1 another constant without a negative sign. I'll leave it that way, but I hate starting off with a negative. So I'll say it's c2 minus that. So that is what y2 equals. Okay, so y2 equals that. That's a second solution to the homogeneous, associated homogeneous equation. Okay. Now we want to find a solution to the non-homogeneous. So we want to solve this. We want to solve this equation right here. How about we just let v equal y prime, which will imply that v prime will be y double prime. So v prime plus y prime, which is v, is 1. This here is separable. V prime is dv dx. I'm going to bring that to the other side. It's 1 minus v. The dv can stay. The dx, I'll move to the other side, bring it on top. And the 1 minus v, I'll pull down there. And then I integrate both sides. The integral of the left side is negative ln of 1 minus v. The integral of the right side is just x plus c. Bring in the minus sign to the other side. That is multiplying both sides by negative 1 gives us negative x minus c. But I'll just write plus c. I'll even call it c1. So e to the negative x plus c1, that c1 can come in front, is equal to 1 minus v. Now, I'm going to move both of those pieces, both of those terms, and I get v is 1 minus c1 e to the negative x. But what's v? You were given a problem to solve in y's, and now you're talking to me about v. Oh, v is y prime. Y prime equals that. Y prime is 1 minus c1 e to the negative x. Okay, so now what I'm going to do is I'm going to separate this or solve this. dy dx is 1 minus c1 e to the negative x. I'll bring the dx up here. So now it's separable and we can solve this. The integral of the left side is just y, and now I integrate the right side. The integral of 1 dx is x, minus the integral of this will become plus c1 e to the negative x, plus a constant. And I will call that y sub 2. Okay, so that problem is done. I want to see one thing very quickly. Let us try yet another problem. Suppose you have that y double prime minus 3y prime plus 2y is 5e to the 3x. And one of the homogeneous solutions to the associated equation is y1 equals e to the x. And we want to find a second solution. Well, y2 is always y1 times the integral of e to the negative integral of p of x dx all over y1 squared times dx. And that's y1. So it's y1 times the integral of e to the negative p of x is negative 3. The integral of negative 3 dx all over y1 squared. So we get e to the x in front. This will become e to the integral of 3x dx. Sorry, it's just 3. What am I saying? Like I said a moment ago, p of x is negative 3. The integral of p of x dx. So what's going to happen is this is just going to come the integral of 3 dx, which is 3x, over e to the 2x dx. So it's e to the x times the integral of this. But that division is just e to the x. And the integral of e to the x dx is e to the x. Times the e to the x in front, we get e to the 2x. So that is a solution. That's the second solution to the homogeneous equation associated to this differential equation. Let us try another one. Suppose you have y double prime minus 4y equals 2. And e to the negative 2x is a solution not to this equation, but to the associated homogeneous equation. And we want to find another solution. And right there is p of x. Another solution, which I'll call y2, is y1 times the integral of e to the negative integral of p of x dx all over y1 squared. Well, y1 is e to the negative 2x times an integral of e to the negative integral p of x is negative 4 dx over y1 e to the negative 2x squared dx. Now that's just going to become plus 4. That e to the negative 2x times the integral of e raised to the integral of 4 dx, which is just 4x, over e to the negative 4x dx okay, and this is e to the negative 2x times the integral of e to the 8x dx. Okay. So we get e to the negative 2x times this integral, which is e to the 8x over 8, which is e to the 6x over 8. And this here is our second solution to the homogeneous equation. Now what if we wanted a particular solution to the given equation? Now you have y double prime minus 4y is just a constant. Now if you let y equal a trig function, sine of x, sine of 2x, tangent x, when you take derivatives, you get other trig functions. And when you take away 4 times this trig function, maybe you'll get 0, maybe you'll get another trig function, but you're not going to get 2. You're not going to get 2. If you try polynomial, so trig doesn't work. If y is a polynomial, you're going to have, and the degree is fairly high. Like if the degree of y was 4, well then the degree of y double prime would be 2. That is, this would have an x to the 4th, and this would have an x squared. Well, when you subtract, nothing's going to kill off the x to the 4th term. So you won't get 2. And if the degree was 14 of y, then the degree of y double prime would be 12. So I know that y is going to have an x to the 14th term plus other terms, possibly. And y double prime will have an x to the 12th term with a number in front in both cases, 3x to the 14th, 11x to the 12th, plus other terms. Now when you subtract, nothing's killing off the x to the 14th term. Okay. But what if the degree was lower? Okay, if the degree is low enough, if the degree of y is, say, 2, well then the degree of y double prime will be 0. It'll just be a constant. So when you do the subtraction, you're going to have an x squared term. So that doesn't work. If the degree of y is 1, a constant, well then the second degree will be 0. And sure, you can subtract the constant from 0 and get 2. You can subtract the constant from y double prime and get 2. Remember, 4 times a constant is a constant. So y can be a constant. Now, of course, y can also be a constant plus e to the x. Okay, because I'm pretty sure that you can cancel, you can get the e to the x's to be 0. In fact, sure you can. Now just add 2 and it'll work. Or negative a half, I think. I hope you understood that. Now, if y is some constant, then y prime is 0 and y double prime is 0. So I want y double prime minus 4y to be 2. For y double prime is 0 minus 4 times y is c, and this is 2. So negative 4c is 2. What do you multiply negative 4 by to get 2? The answer is negative a half. So y is equal to negative a half is a particular solution. Okay, and we can verify that very quickly. If you take the derivative 1 or more times of a constant, like negative a half, you get 0. Minus 4 times negative a half. Does it equal 2? Yes, negative 4 times negative a half does equal 2. How do I know that? Very simply. A negative times a negative is a positive, and half times 2 is 2. So here is a particular solution. This completes the section on reduction of order.